In this video, we're going to look at polynomial functions. So what's on the agenda for today? Well, firstly, we're going to cover power functions and how they relate to polynomials. We're also going to take a look at the most common polynomial that you'll come across, which is called the quadratic, or sometimes referred to as a parabola. And as we do, we'll cover the key terms and properties that you'll need to be familiar with in VCE math methods. So, let's start with power functions. The general form of a power function is ax to the power of n, where n must be a natural number and a can be any real number. The letter x is the input variable. Now, we know this because the function is called f of x. The function is named f and its input variable is x. Any other letters in the function are just treated as constants. That is to say, they don't change over time like the input variable does. The letter a in front of the power function is called the coefficient. The letter n is actually known by a lot of names. Typically it's referred to as the power of the function, but sometimes it can be referred to as the degree or the order of the function. For example, suppose we have the function 2x cubed. Now, we know that the function is a function of x, so x is the input variable. The coefficient must be 2, because that is the term out the front of the power function, and its power is 3. For a function to be a power function, it must be the input variable that is raised to the power of n. For example, f of x equals 2x cubed is a power function because x is raised to the power of 3. If we were to swap the order of those variables, say x times 2 to the power of 3, this would no longer be a power function because x is no longer the variable that is being raised to the power. It doesn't matter what the input variable is, just as long as it is the input variable. So here's another example using an input variable of u. Now, we know u is the input variable because our function is called f of u. Now we can look at polynomials as a whole. You can think of a polynomial as a series of power functions. The general form of a polynomial can be written as follows. Polynomials are typically written in descending order. Furthermore, a polynomial doesn't actually need to have every power from n all the way down to 0. It can actually miss some terms and still be classified as a polynomial. For example, suppose we have a third order polynomial, typically referred to as a cubic. The cubic could look something like this. Notice how we're missing an x squared term? The shape of a polynomial is primarily determined by the power functions within it. In other words, its shape is determined by its degree. Now, there are all sorts of polynomials that we could be looking at, but the most common one that you'll come across in VCE math methods is the parabola, or otherwise known as the quadratic. The general form of a quadratic is as follows. This is the general shape of the parabola. It has a turning point, and it is symmetrical about its turning point. They have 3 coefficients, a, b, and c, and they work together to determine the shape of the graph. The graph that you're seeing now is the graph of y equals x squared. That means that the coefficient a is 1, and the coefficients b and c are 0 because they're not present. Now, let's look at some common features of the quadratic. We'll often be asked to find the coordinates of the axes intercepts. This means we need to find the y-axis intercept and the x-axis intercept. The y-axis intercept is simply the point where the quadratic crosses the y-axis. Similarly, an x-axis intercept is the point where the quadratic crosses the x-axis. Most of the time, you'll find that there are actually 2 x-intercepts. Suppose we have the following quadratic equation. The quadratic crosses the y-axis when x equals 0. You can see this graphically. So, if we want to find the y-coordinate of this point, we need to substitute its corresponding x value, x equals 0, into the equation. This is done as follows. Coordinates are written in the form x, y. In this case, we would write that the y-intercept occurs at 0, -1. This is where things get a little bit trickier. We know that x-axis intercepts occur when y equals 0. But if we substitute the value y equals 0 into the equation, we'll quickly get stuck. We need to use a different method to approach this. There are a lot of strategies we could use to solve this equation. The 3 most common ones that you'll need to know for math methods are using the Null Factor Law, Factorisation, and the Quadratic equation. The simplest approach is to use the Null Factor Law. The Null Factor Law states that if 2 terms multiply together to give 0, then either one or both of those terms must have been 0. Consider the following quadratic. As before, we're going to substitute the point y equals 0 into the equation. Now here's where we're going to get just a little bit fancy. we're going to take out the common factor of x from both terms. Suddenly, we have an expression that is a product of two terms, x and x plus 1. The null factor law states that either x or x plus 1 must have equaled 0 in this equation to get a result of 0. With this in mind, we can now begin to solve the equation. So firstly, let's look at the case where x equals 0. That's fairly straightforward, because x simply equals 0. Now, let's look at the case where x plus 1 equals 0. If we rearrange this equation, we'll find that x equals negative 1. If we look at the graph, this actually tracks with what we see. We see an intercept at x equals 0, and an intercept at x equals negative 1. So finally, we can write the axes intercepts in coordinate form. We can say that the x-axis intercepts occur at x equals 0 and x equals negative 1. Or in other words, 0, 0 and negative 1, 0. Most of the time, we can't just use the null factor law right out of the box. Sometimes we have to work just a little bit harder to get there. Consider the following polynomial. After we substitute the point y equals 0, there's no obvious common factor. So what do we do in this case? Well, we can use a more advanced factorisation technique. We can factorise a polynomial as a product of two terms using the following process. First, we have to validate that the quadratic is in the general form. In this case it is, so we don't have to worry about rearranging right now. The next step is to find two numbers that multiply together to give AC and add together to give B. This is a guess and check method, so I'm going to give you a few tips to get started. I find it easiest to use integers to find the product AC first. This is because there are way less combinations of integers that give the product AC than there are combinations of numbers that give the addition B. Once you have your list of numbers that multiply together to give AC, you can then go through and see which ones also add together to give B. Once we find a pair that work, we can replace the B term in the quadratic with the sum of those two factors. From here, we need to be strategic with our factorisation. We start by finding the largest common factor in the equation, which in this case is 3x. We should now see that the remaining terms in the equation could also be a common factor, even if they need just a little bit of rearranging, as we do in this case. Once we rearrange the equation, notice how x plus 1 is a common factor to both terms. I'll make this explicit by defining it as the letter A. We then take this A term out as a common factor and rewrite the equation as follows. We then substitute the value A equals x plus 1 again to get our equation back in terms of x. Thus, we have written the quadratic as a product of two functions. This means that the quadratic is now ready to be solved using the null factor law. Pro tip: it helps to rewrite the equation so that all coefficients are integers. If you have fractional coefficients, it makes it much harder to find the pair of numbers that we're after. The good news is that we can multiply both sides of the equation by any number we want in order to get this to happen. Now, this is especially useful because the right-hand side is 0, because we're solving the case where the quadratic equals 0. So we can choose any number we want and not mess up the equation. For example, suppose we have the following quadratic. We can multiply both sides of this equation by 20 to get all the coefficients as integers. This makes life so much easier. One of the issues with the previous method is that at the end of the day, it's a guess and check method, and that can be quite time consuming if you can't find the magic pair of numbers. Furthermore, there's no guarantee you'll even find the right pair of numbers because the quadratic might not even have any x-axis intercepts. So what do we do in this scenario? Well, when all else fails, we can use the quadratic equation. The quadratic formula is as follows. This assumes that your polynomial is in the general form ax squared plus bx plus c. When we substitute the coefficients of the quadratic into this formula, one of two things is going to happen. If the quadratic has x-axis intercepts, it'll tell you where they are. If the quadratic has no x-axis intercepts, you'll find out pretty quickly because the input to the square root term will become negative. And in math methods, this is considered an invalid result because you cannot have the square root of a negative number. By now you should be pretty familiar with the shape of the quadratic equation. You'll notice that every quadratic we've seen so far is symmetrical about its turning point. This is also referred to as the axes of symmetry of the quadratic. You can find the axes of symmetry with the following equation. For example, suppose we had the quadratic equation f of x equals 2x squared plus 4x plus 3. Step 1 is to ensure that the function is written in its general form, which in this case it is, so we're good to go. Step 2, substitute the coefficients into the equation and thus find the axes of symmetry. If we use this function as an example, we'll find that the axis of symmetry occurs at x equals -1. In the previous example, we found that the axis of symmetry occurred at x equals -1. This is actually the x-coordinate of the turning point that we are after. If we want to find its corresponding y-coordinate, we now need to substitute the value x equals -1 back into f of x. And if we do so, we'll find that the turning point occurs at -1, 1. The turning point form of a quadratic is as follows. This is simply just another way that we can express quadratics. You'll need to be familiar with this form because your test won't always give you quadratics in the general form. It's called the turning point form because the values h and k give you the turning point of the parabola, where h is the x-coordinate and k is the y-coordinate. For example, if we have the following quadratic in turning point form, we can immediately say that the turning point occurs at 3, 4. So how do we convert from the general form to the turning point form? We can use the technique known as completing the square to achieve this. We do so using the following procedure. So let's step through it with an example. First, we take out a as a common factor. This gives us a new quadratic to work with. So using this new quadratic, we are going to add and subtract the term b squared divided by 4. This is totally legal in math because we are adding and subtracting the same number. This is where we need to be very particular. We have created yet another polynomial which we want to factorize. Specifically choose the positive version of b squared divided by 4. We then want to factorize this new polynomial as a product of two identical terms. This isn't quite yet in the turning point form. If you notice from before, the turning point form is actually x minus h, not x plus h. So we need to do a slight bit of rearranging to ensure that we have our signs in the correct order. Having done this, we've achieved turning point form. Now, we can simply say that the turning point must occur at -1, 1. And that brings us to the end of our exploration into quadratic equations. If you found this video helpful and would like to see more, I actually have a Google Drive with written versions of these lectures covering the entire Year 12 Math Methods syllabus. I've made these resources available for free on my website. Just click the link in the description below and it'll take you to my website. Just scroll down a little and click this heading to get access. No opt-in required, free of charge. This video was a deep dive into quadratics, but those aren't the only polynomials out there. So in the next video, we're going to cover polynomials more generally. See you there.